lot of what we are talking about today is just a brush overview of things. If you take AP Chemistry, they'll have to go into it a lot more, but for Chem 1, just a brush overview, okay? So we have been using balanced equations for a very long time now. They give us a lot of useful information, but the balanced equation doesn't tell you everything about the reaction, okay? It doesn't actually tell you how it occurs. So this is going to kind of look like a little bit Hess's law from last chapter, but we're not actually doing that this time, okay? So an elementary reaction is a reaction in which the reactants are converted to products in a single step. So most of the time, this is what we see, okay? But for an actual chemical reaction, it will make up, or it will have like 2 or more of these elementary reactions to make up the overall what happens reaction, okay? This is where it starts to look like Hess's law. So this series of elementary reactions, or steps that take place, we call the reaction mechanism. So it's a lot more complex than what we see to our eyes. Did everybody write down their 2 for the line? With our series of steps with the reaction mechanism, we have what are called intermediates, which are what, if you remember in Hess's law, do you remember how we could like cancel things off if they're on opposite sides? Intermediates cancel out. Okay, it's a product from the first step that it appears in, and then it's used as a reactant in the next step, and it gets used up. So an intermediate has a more stable structure and a longer lifetime than an activated complex, but it's not going to show up in the overall reaction because it's only reactive enough to take part in the next step. It's not going to stick around for very long, okay? They don't appear in the overall chemical equation when you write the whole chemical balance equation out. So on the next page, I have an example of a reaction mechanism to see where it's a multi-step reaction, and they don't progress at the same rates. So one step will be slower than the others. The slowest step, so in your series of steps, it might say like slow or fast or something like that. But the slowest step will determine or limit the rate of the overall reaction. So this is a 2-step reaction. I don't have very much written down. I mean, I'm going to say some more things out loud that is not on the page. First of all, we have to let's look for an intermediate. Okay, so the intermediate shows up on the product side in step 1, and it's used as a reactant in step 2. There's one intermediate for this reaction set. So what's the intermediate here? What could be canceled out? Like if we were adding them together to make the overall equation, what can be canceled out? The O atom. Right. Right here. This O right here and this O right here. Those are signifying our intermediate. Okay. So it's formed and then used up instead of being in the overall reaction. Okay. To get the overall reaction, it's just like Hess's law where we add them together, but we're not dealing with the changes in enthalpy, so we don't have to deal with all those numbers and stuff this time. Okay. With this, so you see how it says slow and fast? The slow and the fast are good indicators of what we call is the rate determining step. Okay. Because the reason why number 1, step 1 is the rate determining step. And that's because you can't get to step 2 unless you form that intermediate O. Okay? So step 2 cannot take place unless the intermediate O has been formed. And so then if step 1 isn't happening, or it's happening at a very slow pace, then step 2 has no way to start. So the reaction can't go until step 1 has gone. Okay? If you would want to speed up the overall reaction, like we were talking about back last week, then you would have to maybe put in a catalyst, heat it up, do something, so that you're speeding up step 1 to make that go faster, so then step 2 can also go faster. Okay? It's very complex. In AP, they have to guess, like they have to like look at a bunch of things and guess what it's going to be. But here, you just need to know that if it's slow or very slow, like if it's very slow versus slow, the very slow is going to be the rate determining step. Okay? Or just think about what are my intermediates and what cannot happen until that intermediate has been formed, sort of thing. Okay? Reversible reactions. We've been talking about reactions in the forward sense all year. Okay? Where you're going forward to make the products. We have reversible reactions where you can actually make the products turn back into reactants. So, I have this example. This arrow, this picture isn't that great, but you have to draw your own in. So, you have, like, it's like those half arrows we used to do back in chapter 5 with orbital notation, except they're turned on their side. And the top one I have is pointing towards the forward reaction, and the back one is pointing towards the other way. And so what that signifies, it's called an equilibrium arrow. It's signifying the forward reaction would be the 2SO2 plus O2 makes the 2SO3. But then the backwards reaction then would be you could have your 2SO3 that turns into the reactants. So this is something that we don't think about because normally when we do a reaction we only see the products present, or we don't see the reaction occurring anymore. Well, when we get in these reversible reactions we have what's called equilibrium, where it's a dynamic state that things are happening all the time. We just personally can't see them with our naked eye. Okay? So with these forward and reverse, this is a picture. So the left picture is our reactants, the SO2 and the O2, and that's all there is present. If it would go all the way to the product side, all of the reactants would turn into products, so we'd have the SO3 present, and that's it. But then when this starts to come up, then it goes back into the reactants. And so the middle shows how you can have the reactants present and you can have the products present. Okay? So it's the forward and reverse reactions happening. And this is what happens all the time. We just can't see it. Okay? So this is what's called equilibrium. At the beginning of the reaction, the forward reaction takes place because only the reactants are present. It's the only thing that can happen. So the reverse reaction has a rate of 0 at the beginning. As the products begin to form, the reverse reaction can then take place. So the rate of the reverse reaction starts out slow, but eventually it reaches the same rate as the forward reaction. So when the rates are equal to each other, we say that this has come to a state of balance that we call chemical equilibrium. Okay? So I have these two graphs. They are kind of a good illustration of what happens. Notice how the x-axis for both is time, but on the y-axis it's changed. Okay, so you're going to have questions about this. The top one, or your left one, is rate, and then the other is the amount. Talking about the amounts, okay, at time equals 0, the reactants have a bunch of stuff, and the products have 0 at time equals 0. There's nothing in there. Okay, this is like the concentration. So if you want to label this as the concentration graph, that might be good, because you will have questions about this kind of stuff. Okay, so at time equals 0, we have only reactants, 0 products. So when that happens and we only have reactants, then the forward reaction can take place. Well, as the forward reaction takes place, the reactants then lose how much they have, and the products start to gain some. But then once the products start gaining, then there's products present, so then I can do the reverse reaction. And so this is where it's like a cycle, where the forward and reverse reaction are going and going and going until they even out. Okay? And when they even out, somewhere in here, when they're parallel, they're not changing, they're not going up and down anymore, we say that equilibrium has been reached. So at that, where I just drew that line, that's where the equilibrium is now. Because at equilibrium, the reactants and products will not change their concentrations anymore. Okay? They're going to stay constant. On the top graph, we're talking about the rates only. Same thing. At time equals 0, there's only reactants present, so we can only do the forward reaction. At time equals 0, there's no products, so the reverse reaction can't take place. But as you keep going in the forward, you make the products, so then the reverse can start. And over a period of time, then the rates become equal. When the rates become equal and they go into one line together, that's saying that the equilibrium is reached right there. Okay? So you will have questions where it says, it might be like a true or false question, because this always chumps up my AP students, so we'll probably jump you too. I'll say true or false. The concentrations of the reactants for products are equal at equilibrium. And that is false, because the concentrations are constant, but they don't have to be equal to each other. The rates will be equal to each other. Okay? And so these graphs kind of help illustrate that. So at equilibrium, your components don't change when they have reached the equilibrium. The chemical equilibrium is what we call a dynamic state. So it's constantly going forward and reverse reaction. We just personally cannot see it anymore. Okay? And that's because their rates are equal, so no net change can occur. So although the rates of the forward and the reverse reactions are equal, the concentrations are usually not, and that's where that graph is, and they're separated. Okay? The relative concentrations are what mark the equilibrium position of a reaction. So this tells you whether the forward reaction or the reverse reaction is more likely to happen, which one is favored. So here, if it's a higher concentration of reactants, that means that the forward reaction is favored because it wants to get rid of those reactants. And so this is just a different way to draw that equilibrium arrow, where the top side is longer than the bottom side. And so when the top side is longer, that shows that the forward reaction is favored to make the products. But then if the bottom is longer, then that is showing that there's too many products, so the reverse reaction is favored, so then it can make the reactants instead. Okay? Last thing to talk about. Although all reactions are reversible to some extent under the right conditions, we don't always see that. Okay? So one set of components is often favored in the equilibrium, and then the other one can't be detected. So normally what we see when we do labs is we can say that we start with the reactants, and then it goes to the products. Like if we form a precipitate or something, we see the precipitate in there, and that's just, okay, we're done. So when it is favored to go to the forward reaction, and you don't see any reactants being reformed, then you can say that it's gone to completion, or it's irreversible, it's done. And then when no products can be detected, so if we added two things together and nothing happened, we would say, normally we just say no reaction. You can say no reaction can take place, because that's what we're seeing. But that just means that the equilibrium is so much more favored so that the reactants just stay how they are. Okay? So that's it. On the packet I gave you, 1 through 4 can answer questions about this.